Hello, welcome to Virtual ITSEC 2020 and the tutorial entitled Live Virtual and Constructive, or LVC Interoperability 101. My name is Kurt Lessman. I'm the co-founder and CTO of Tritium Corporation, and my co-presenter is Mr. Damon Curry, Business Development Extraordinaire at Pitch Technologies. So let's get started into our tutorial. So, talking about the agenda, we'd like to first cover the learning objectives that we have for this tutorial. Then we're going to start with an LVC interoperability overview. What are the terms that we use? What are some of the terminology, the technologies, things to start getting you used to understanding what LVC is and how to use it. Then we're going to talk a little bit about standards. There's been an awful lot of activities out there about standardizing the processes and the protocols used for interoperability. Then we're going to talk about interoperability using something called a gateway, and we're also going to talk about cross-domain solutions, both very useful tools when dealing with interoperability and interoperability in environments that have both different levels of classification. Then we're going to wrap it up with an LVC interoperability use case. We feel that having a use case is really a good way for us to describe how you can use LVC, some of the processes, some of the tools in an actual use case. And then we're going to have summarize what the information we provided in the tutorial so that you can use it can be used in the future. So first, let's talk about learning objectives. This tutorial is really focused on managers who need a top-level understanding of live, virtual, and constructive interoperability. What does it mean? How can they use it? How can they employ this technology to help them in their program? And so this tutorial will provide an overview of recommended concepts, processes, and tools needed to achieve interoperability. I already mentioned the use case, so we'll talk about that use case that demonstrates interoperability solutions that meets a military training need. And then we'll have a summary with recommendation. The objective of this tutorial is to provide the managers and those new, they don't have to be a manager, but those new to the LVC technology, the insight needed to support intelligence decision-making when encountering either the need to use interoperability or a decision if LVC interoperability is right for their project. So let's first talk about LVC interoperability overview. We're going to talk about simulation definitions, then live, virtual, constructive interoperability definitions. There are two different sets of definitions. And then we're going to talk about a distributed environment overview. That's a picture that describes all the different things you need to do so that a complex distributed simulation environment can be integrated and used. So first, let's talk about the LVC interoperability overview. First of all, what is a simulation? PEO Stry used to say the term that everything but war is simulation. Well, that's true, but in this case, we're going to talk about simulation as a software model that runs over time, and the over time part is the important aspect. Simulation interoperability. So it's the ability of connected systems to communicate and function together. And a lot of times when you bring these systems together, sometimes they weren't intended to work together, and then you have a new and enhanced capability by bringing these disparate simulations together. These interoperable components can be combined to create an application, and applications can be composed to create a system, and a system can be combined to create a system of systems. So think of building blocks. You can build one on top of one another. So first of all, let's talk about live, virtual, and constructive. I'm sure you guys have all heard LVC. So what is that? Let's start on the left-hand side, live simulation. When we say live, that is real people operating real systems. And for the context of this presentation, we're going to be talking about real military systems, weapon systems. So you have real environments, real systems, real people, and it's in real time. You know, once a missile was fired, you can't stop the clock and say, oh, wait, let's go back. So everything is live and on wall clock time, it's called. So the next one is virtual simulation, real people operating simulated systems. So there's various different kinds of platforms and simulators. There's usually a virtual environment, and it is also run in real time. As an example, there's a picture here of a gunner in a tracked vehicle. It's much easier and more cost effective to have several simulations of that tracked vehicle for a gunner to operate in, instead of having a gunner going to a range and actually driving that tracked platform around in either a test range or a training event. So this is a cost-effective mechanism so that we can use simulated tracked vehicles, but it has the same look and feel to the operator as if it's a real one, but it's still real people. And we also say it's a virtual environment, since it is a simulation of the live system. That virtual environment needs to stimulate that simulation as if it were in a live event, whether it's in a test event or a training event. So there's a real person sitting in a simulated environment, and then all the sensors on that system is being stimulated with virtual information, kind of like looking through a virtual lens and looking at a virtual world that is very similar to the real world. And so finally, constructive simulation. It is simulated people operating simulated systems. So this is where you get into computer-generated forces, CGF. A OneSAF is a large Army simulation that generates simulations of weapon systems and it aggregates level from the singular entity all the way up to a battalion and higher. It also has a virtual environment. So these virtual entities are acting and reacting to the virtual environment that is designed to replicate the real world. And then with the constructive simulation, you can actually go faster than real time or slower than real time. That's one of the beauties about constructive simulation. Whereas everything else, when there's a live person or a live system in the loop, everything is real time. And when I say real time, that's wall clock time. So that's one of the differentiating factors about constructive simulations, is it can be run faster than or slower than real time. So let's talk a little bit about distributed simulation. A distributed simulation is a system that is basically having multiple processors that is executing on one or more computational nodes. What that means is you could have two processors on a laptop or on a workstation, and there could be a simulation on one and a simulation on another processor, and they have to communicate. Just like if there was a simulation on a workstation and there was a network to another workstation in Walla Walla, Washington, and those two workstations and the simulations on those workstations had to communicate as if they were sitting right next to each other. So how that happens is the simulations are able to interoperate using a common services or a common protocol with some rules over a network. We're going to talk a lot more about that. So simulations can be distributed over a number of different components, ideally loosely coupled or federated. This allows growth over time, allows components to be replaced or upgraded easily, and additional computational power is needed. What this is getting at is if you just have one simulation and all the entities, the LVC entities are represented in one big simulation, if you ever need to make a change, you have to bring the whole simulation down. When you have it federated, and it's a loosely couple of simulation, a simulation can come in and out of the environment as needed, and you don't have to bring the whole system down. So distributed simulation, this technology can be used to support the wide variety of things, from warfighter training, command post exercises, enhanced modeling and simulation objectives, research development and test and evaluation, and other systems like other reasons for like logistics and other things like that. So distributed simulation is a very powerful tool that allows you to use other simulations, other LVC assets that you might not even own, but you can work with those other systems so that you can create an environment that can support either a more advanced test or a training event that you and your organization are able to carry out. So it leverages the power of a lot of people and a lot of assets from across the DoD. So what is a distributed event? Let's look at the very bottom of this. We've talked about what LVC systems are. We've talked about the interoperability to allow live, virtual, and constructive systems to talk together. So we have this ability to have these simulations and live components talk to one another. And you have to stimulate all those either in the real world, like if there's a sensor on a weapon system, it can be stimulated with the real world, or a virtual representation of the real world. And that's what stimulates virtual and constructive systems. And then when you run that over time, that's when the real power comes in, is that you're able to create this complex live, virtual, and constructive event to achieve your training objectives using a vast variety of different LVC systems out there, some of which you control, those different other organizations control, but you can all come together and work together to achieve common purposes. So how are we able to do that? What are these interoperability requirements? So first things first is an ability to meaningful communicate. We need to have a common language that describes the LVC system. As we're talking right now, we're using the English language to be able to communicate. So that's, the simulations have to have something like that. They have to have a standard way so that they can send and receive data that's meaningful to them. Well, to receive and send that data, there has to be an ability to distribute that information that has well-defined rules, or some services provided by another software application that allows you to send data back and forth to all the different simulations out on the network. And then network, that's the bottom piece. You have to have a reliable network. Nowadays, networks are very reliable and very robust, but in the early days of LVC, that was really a challenge. But now we pretty much take that for granted, and there are a lot of different networks out there that your organization can leverage. So you also need a common context. So as an example, we use the example of we're using English, the language of English, maybe with a little bit of a Southern drawl here, to communicate this LVC interoperability tutorial. Well, it's not just English. We have to have an understanding of a context of the words that I'm using. And that comes with, over time, from a person, your life experiences. Well, simulations right now don't have life experiences, so they have to have a common understanding of the meanings of the words. And they have to have a common understanding of the environment, of that virtual environment that we talked about earlier. And time has to be something as simple as what is the current time that I'm at now, and how does that relate to what's going on in the virtual environment? So you have to have all these different bits, processes, standards, protocols, different services to allow all this to happen. And this has been going on for a good 20 years, about getting all this defined and then proven through years of experimentation and results. So one of the things you hear an awful lot about is reusing software and composability. So reusing software, we said it earlier, every DoD organization cannot develop every single simulation of all the other systems out there that their system needs to communicate with. And so when you can reuse another simulation that was developed by a different organization, that reduces the cost on your side, and it also reduces risk, as there are others that have a solution out there that you can use. Composability is another word that we use a lot. If we all have ability to meaningfully communicate in a common context of the information being passed, you can use smaller simulation and build those up and compose a more complex environment and simulation of the environment, as opposed to just having one of the smaller composable pieces. So well-defined software interfaces and the access to those reusable components is critical. The ability to replace models at the component level without interrupting the larger system or requiring software changes or recompiling of other systems is key. And we're going to talk about how LVC allows that to happen. So when you're starting to look at LVC and you're starting to look at interoperability with other organizations or with simulations that you have within your organization, there are several things that you need to talk about. Yes, there is the LVC folks in the room. That's a unique language and skill set that takes time to understand and adopt. And that's one of the reasons we're having this LVC interoperability tutorial, so more people can understand these terms and processes. So some of the discussions that you'll hear when you start talking about interoperability is, starting at the top, what is the information data exchange model? We're going to talk a lot about data exchange model. They're also called object models. So which coordinate systems are used? Local tangent plane, geodetic, geocentric. There's going to be all kinds of different coordinate systems that each simulation has to understand and convert to their coordinate system. What algorithms are used? Which ones need to be shared? Which ones are unique? Which ones may be protected by intellectual property rights? And how do we still use the function of that simulation without exposing the details of somebody else's intellectual property? What is the representation of the environment? What is used? It goes back to how we're going to virtually represent a live world, and how are we going to stimulate these simulations and live systems the same way. What about time handling? Are we going to stop this event at any time? Are we going to restart it? What's the scenario going to look like? What are the object model names? What are the object model types? What's the logic sequences of interactions are required? You've heard like time-ordered event list. It's a list of things that go through an order that help set the stage of a series of events to make sure the LVC event goes properly. There's also measles out there that are very similar. What is a conceptual model of the entire exercise? We have to have an understanding across all these different organizations of what we're really doing here and why we're providing the data, because that context is important as we start digging down deeper into the data necessary to distribute between all the different LVC systems. So we talked about an LVC distributed event environment. This graphic I use from our friends at JMedic, the Joint Mission Environment Test Capability. JMedic, I mentioned earlier, there are various networks that are out there that connect a lot of different locations and labs and facilities and test ranges and training ranges together. JMedic is one. They're focused on the test side. They connect all the different test ranges across the country. They also connect it to different prime contractors locations and other DoD locations as well. So they have an established network that people can use. So think of this as a layer cake. Let's build it from the top down. So we have all these different programs of record, and they want to use and set up an LVC distributed environment so that they can either do training on their weapon system, or they can do testing on their weapon system. For that to work, they need a tactical network emulation. So they need to either have the actual tactical network that the weapon system requires to communicate at the tactical level, or a simulation of that network to allow simulations of those message traffic being sent back and forth to be sent. Then underneath that is we need a virtual and constructive red and blue system simulations. So we not only do we have to have a representation of blue forces out there, we also typically have to have representation of opposing forces and different simulations out there to accurately model the behavior of the opposing forces so we can evaluate the effectiveness of our weapon systems. Then you have a mission-based scenario, and then you have this systems integration. And this is where you'll find things, and we're going to talk more about this later, a lot of series of interoperability solutions called distributive interactive simulation, TINA, test and training enabling architecture, HLA, high-level architecture. Those are the solutions that communicate with the different simulations that enable interoperability. Well, then underneath that, you have to have a support network. That's where JMedic comes in. That's where J10 comes in. I also list cross-domain solutions here as well. That allows data, the right data to cross from a higher level classification down to a lower level classification. It's got to follow a set of rules. That's where you also receive gateways, where there's conversion between one interoperability solution to another. Well, then you have to have data collection. I mean, without collecting data in a meaningful way, so you can do real-time data analysis and after-action review data analysis, well, what's the point of doing an LVC event? So you have to have a plan and the systems available and working to be able to collect the data from a performance perspective as this LVC event takes place. Well, then if you use cloud services, you need to have connectivity to the cloud. Then there's these common tools. There's lots of different event management kinds of tools. There's pre-event planning tools. There's post-event data reduction, analysis, and visualization. And all these different tools your team will work with to be able to design, execute, and assess the data from the LVC event. And a lot of them are based on the different interoperability solutions that we'll talk about in a little bit, those being TINA, DIS, and HLA. And at the bottom, you have to have standard processes and procedures. Having that in a documented fashion enables repeatability, it enables scalability, and it lowers your risk of being able to interoperate between all these different systems. So these are all the different layers required to put together a distributed event environment. So let's talk about interoperability through standards. What's the value of standards? What is the standards? Past and current interoperability standards. Hey, we're going to talk more about this, DIS, HLA, and TINA. And we're going to recommend an LVC integration approach that is also a standard. And that process is a good one to look at for your team to step through, to walk you through the process to be able to make these LVC systems interoperable. So the value of interoperability standards. So often, particularly in the past, not so much now, but people would look at their own unique requirements and they would develop their own mechanism for interoperability within their organization. And the problem is that every organization had a standard that typically worked pretty well for them, but when they went to work with somebody else, another organization, it didn't work because the protocols and the processes and the tools were really focused on their own requirements and not a broader set of requirements. But it worked for them. So one of the things that the standards community came about was we really needed open standard solutions. We needed common data models. We needed common, I've mentioned that earlier, object model. We needed application programmers interface. It's the software that our programmers can use so that they can use common services to be able to be interoperable with anybody else who use that same data model and API and a common processes. So by going through open standard solutions, it does away with the stovepipes, and it's good for everybody. And when you start using LVC for the first time, you are leveraging many, 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 many years worth of blood, sweat, and tears of developing these data models, these APIs, and these integration processes. And you can leverage them without having to go through that pain. So there's different technical aspects and business aspects of interoperability. Some of the technical aspects: enable efficient distributed simulation. So we want to have a mechanism that you have, you can handle the throughput, there's minimal latency, and it's scalable to the scope that we're looking at now. It can support simulation-specific requirement. It's not just limited to data distribution, but it can provide common services like doing remote method invocation, time management, being able to stop and start time as needed in a constructive environment, ownership control, basically passing ownership of representing an entity from one simulation to another. Those are some of the common services that are out there. And you also want to isolate simulators from the physical transport mechanism, meaning the network, and you want to avoid that technology lock-in. Well, there's a lot of technical reasons to be able to that you want to leverage and apply to as these standards were built. But there's also a business aspect of why you want to use standards. I mentioned it earlier. You know, if you want to promote interoperability and reuse, don't develop something from scratch on your own. Go to a standards body and leverage what people have been using for the past 10, 20 years. These are proven commodities that you guys should leverage. They're vendor independent. A lot of them are vendor independent. Come up with standards, and different organizations that you can that are either COTS that you can buy or GOTS that are government provided that you just use. And they're domain neutral, meaning if one was designed for the training environment, these standards bodies have spent so much time on it, they've tweaked it so that now these standards will work in training, test and evaluation, research and development, etc. So interoperability, what we've done in the past for interoperability. Well, before that, an organization would standardize on a vendor solution. And that was, the 20-year ago approach. It's like I'll go to a large or go to a vendor and say, build me an interoperability solution. It typically was optimized for a specific need, meaning it probably isn't composable and reusable for others. And it created a vendor lock situation for the government. So the government always had to go to the same vendor to make any changes. And now more and more the government is looking for open standards and allow competition to write software using the open standards as opposed to a proprietary vendor lock situation. Or folks used to standardize on a programming language. Again, it's typically on a specific need. It's kind of like saying, okay, well, if we all use C++, that would be a good start of being interoperable. I don't know if you guys remember this, but there used to be a mandate to use Ada for everybody in the DoD. Well, that didn't work out so well because Ada doesn't work for everybody. So that doesn't seem to work out so well. And when you do these things, it's awfully hard to incorporate new technologies into your system, like service-oriented architecture, cloud-based solutions, different scripting languages. So when standardizing on a vendor and standardizing on a programming language, it was adopted when reuse, composability, and interoperability were not high priorities. But it was cutting edge. So modern interoperability approaches. First, we want to standardize on the data model. The data model is that defined network protocol or message format. It is all the information listed so that a sender can populate a message in a common way, send it over the network, and someone who receives that can understand it and read it in a common way. So the intent is a lossless data transfer. So it defines all the data that's needed to interoperate. You also want to standardize on a software application programmer's interface, API. It provides that software interface to all the different interoperability solutions and services to enable interoperability. So if you have an API to join a federation, or if you have an API to start time, stop time, to create an instance of a tank object, a tank class, that's where an API comes in. And then you standardize processes to leverage the data model and the API so that you have repeatable and consistent ability to integrate these LVC systems. So let's talk about data models. It's to enable the semantic interoperability among simulation applications. It provides that common language that all simulation applications need to use to communicate. And so there's some reuse in terms. There's data models is the same thing as an object model, which is the same thing as a data exchange agreement. And what it is, it's like when we're communicating in right now, we're using the English language. There's we understand what those words mean. I'm transmitting those words over the air from my mouth to your ear. That's the transport mechanism. So this data model is a document that describes all the data that will be exchanged. A lot of times you want to represent something in something called TSP, time, space, position, information. So it has time, it has the location, it has the orientation, it has velocity, it has acceleration, it has all the information about it. But that's just the basics of what it is and where it is. But there's color, there's articulated types, there's enumerations, there's the amount of rounds that the weapon, how much fuel it has, all kinds of information. But what that does is if everybody has a common understanding of what this data model is, if I'm telling you about my airplane and sending it over the internet, and you receive this packet and opened up, you know it's an airplane. So that's the importance of what data models are. APIs are the same way. It's a software interface to software services that enable interoperability. So it allows your programmers, the people who actually communicate with the LVC systems, the ability to leverage the services offered by these interoperability solutions like time management, quality of service, ownership management, data distribution management, and remote method invocation. These services have made a significant enhancements to LVC interoperability. Understanding these and implementing them using common practices improves performance and reduces the risk as you put this environment together. So we've talked about the data models, we've talked about API. Well, now we need an integration process, and that well-defined integration process is critical to success. And that's one of the first things you need to do when looking at this and adopting LVC technologies is you need to identify and adopt a proven process to support the design, the integration, the execution, and the assessment of the environment. And you need to ensure the environment is designed and configured to meet the event requirements. So a structured process is necessary, and there's several of them that are out there. Don't risk your program by trying to wing this part. So open standards. According to the Software Engineering Institute, a system is open if it's fully defined, available to the public, and maintained according to group consensus. So there are several organizations that have standardized interoperability solutions, and here's a few of them. The Institute of Electrical and Electronics Engineer, IEEE, Simulation Interoperability Standards Organization, CISO, and the TINA Architecture Management Team. These are 3 different organizations that have standards that you guys can leverage. And oh, by the way, you can pick one of these different solutions, and there are mechanisms to allow you to be able to communicate using these different protocols. So what are those 3 protocols that we're going to talk about, the big 3? One is Distributive Interactive Simulation, DIS. It's an IEEE standard 1278. I forget what version they're on now. It is a protocol standard. It is really focused on making sure everybody understand what data is sent over the wire so it can be sent properly and received properly. And it's mainly sent by broadcast and multicast UDP best effort. The big focus is the interoperability standard is the data model. After DIS came along, the high-level architecture, IEEE 1516 and NATO's STANAG 4603, their interoperability standard was all about the data model, very similar to DIS, but it also has the API and a standard process that we've talked about. And then another one called Test and Training Enabling Architecture, TINA, their interoperability standards was the data model, the API, and the process as well. The bottom one, TINA, not only did it define the architecture and the standards, it's a government provided solution. So it also is a GOTS product. Everything that TINA develops, government can use it for free. So there is an API standard. They have auto-generated software to make things easier to use. It also has a standard object model and it has middleware services, just like HLA. So with that, I'd like to hand this over to my colleague, Mr. Damon Curry, and he'll talk to you about interoperability versus interconnectivity. Damon?
Hello, everyone. Thanks for your time. We'll look at interoperability versus interconnectivity and try to distinguish these terms. It's a little tricky, but the concepts are important in simulation. So LVC interoperability requires data exchange with other systems without requiring modification to those already connected systems. Therefore, the connections can be very flexible and they can grow and change over time. Interconnectivity sometimes implies data exchange protocols that do require system-wide changes. Now, these are not absolute guarantees in all cases, but this seems to be the general description of the distinction between these terms. So in some cases, it will require recompilations of source code or relinking to new software libraries in order to implement some specific connections instead of very flexible connections that may be implemented on the fly. There are many, many data messaging methods in use. I wouldn't be surprised if there are an infinite number of them. Some of the examples are Google Protobufs, CAN bus, which is used in automotive primarily, Link 16 messages for air-to-air and air-to-ground messaging of military systems, DIS, HLA, TINA, and DDS. And you'll see DIS and HLA and TINA are specific to simulation, and TINA also simulation, especially for equipment and system testing. And DDS is an Internet of Things type of system. And you see the checkboxes here where we try to show which ones lean more on the interoperability side, which is generally the more flexible side towards LVC and simulation connectivity, and the interconnectivity side, which is more about taking 2 or 3 or 4 or n number of systems and making them work together. So data distribution service is a type of interconnectivity system that has many similarities to HLA and TINA. So we'll provide a little more detail here and try to clarify some of the terminology and the details. It is an API standard available through the Object Management Group, OMG. It's meant for real-time interconnectivity of systems exchanging data via the DDS standard. Its most common application is for Internet of Things, making devices connect together over the Internet to enable interconnected systems to exchange data. DDS uses many similar concepts as TINA and HLA, and you'll see those here. A publish-subscribe architecture is common, and a data model, whereas HLA has something called a federation object model, or a FOM, and DDS calls a similar sort of a construct a data space. It has its targeted use, DDS, which is interconnectivity or Internet of Things. It does not provide runtime interoperability services like time management as HLA does. It cannot be used in place of HLA, but it could be used in conjunction with HLA. So sometimes you'll see them described where DDS and HLA are used in a complementary type of context, and in other cases, they'll seem to be in an opposing type of context. One item that's often confused is just the terminology. HLA has a runtime infrastructure, or an RTI, and there's no similar construct in DDS. There's no central RTI in the DDS system. However, the best known company that provides DDS software is a company called Real Time Innovations, whose acronym is RTI. So in one case, you have to be careful with the terminology because you might be talking about an HLA runtime infrastructure when you say RTI. And in another case, you might be referring to the company that makes DDS software. Let's take a look at a timeline of interoperability standards, looking back at the bottom of the page, all the way back into the 1980s, early 1990s, when the first U.S. Army systems came together, branched off into DIS and ALSP, which then kind of merged back together to form HLA in 1996, where lessons learned were applied and put together in a publish subscribe architecture. It was soon recognized that it was necessary to have a special version for equipment testing to have those special features and capabilities involved, and so along came TINA, and you'll see that TINA is branching off to the left there and is now up to TINA version 6.0.7. HLA has continued to evolve, so there's a 2010 version, the NATO standard FOM, which is called the NET-N FOM, or NATO Education and Training Network FOM, came along in 2013. Just recently, a space FOM has come along and been standardized by the Simulation Interoperability Standards Organization, and that space FOM has been standardized since 2018. And soon HLA 4, often just called HLA Evolved 4, is coming along roughly at this time frame right now. DIS has moved also from its days in the 1990s up through several versions through version 7 in 2012. And then I indicate here sort of a dotted line branch over to DIS version 8. The dotted line branch indicates that there is some disconnect or incompatibility there. DIS version 8 is not necessarily backward compatible to all the features of previous versions of DIS. So in some ways, it's a continuation of DIS, and in some ways, it's some new work. But that's the timeline of those standards. Let's look a little more detail at DIS, or the Distributed Interactive Simulation, and keep in mind that this is the first attempt, the historical first attempt at establishing a standard for connecting simulators and simulation-based devices together. So DIS applications run, as indicated by those orange boxes at the top, across a network, exchanging data across a computer network. The DIS standard, also referred to as the IEEE 1278 standard, is an over-the-wire specification, meaning that it is standardized at the level of the data that's actually moving over that network wire. So DIS actually defines the structure of data that's sent over the network using something called a protocol data unit, or a PDU. It is a binary protocol where the individual bits are defined and the bit order and byte order is mandated. It defines the behavior of message handling. So receiving participants must review each packet for applicability. So each system sends out its data updates, and all receiving systems must review that data and determine if that's of interest to that system. So if we look in a little more detail, we look here in the upper right at the entity type identification example within DIS, you'll see this is a hierarchical designation of entity type, and these enumerations, as they're called, are listed in the CISO reference standard document. So here we'll see that 8 bits have been set aside to provide a numeric value to indicate the entity kind, such as a platform or a human or something. Then there's 8 bits set aside to indicate the domain, and then the country. A domain might be air, space, ground, underwater, etc. Then a country has enumeration, category breaks it down further, subcategory breaks it down further, and then specific and extra enumerations are provided as well to get into great detail. So it's possible in the DIS standard to break this down into very specific definitions of entities or simulation activity going along on the network. DIS does not include an API or implementation details or solutions. It doesn't provide the source code for you to do that. There are examples, of course, that are available. But in the standard itself, it's defining the nature of the data that's moving across the network, and each system must conform to that standard. DIS follows the commercial off-the-shelf and open source business models so that it's available to anyone, and there are commercial companies that provide tools for use with DIS. DIS is primarily focused on military systems and requirements. This is very important if you're going to do something non-military. And an example I can give is if you're trying to simulate combat systems, for example, then DIS will already have in the standard probably all the definitions and enumerations that you need. But if you want to go into a different area and go into medical, for example, or transportation, or maybe space or something else, then you'll find that the enumerations that have developed over the years for military combat applications will not be so applicable. And in that case, you'll probably be forced to implement a lot of what's referred to as custom PDUs, which have their own concerns about the use of too many custom PDUs, and we'll come to that. DIS participants must broadcast or multicast the data on a local network using the UDP network transfer protocol. That's also important. It means that each system has to transmit all of the data that it wishes to update to the outside world. So if we have a flight simulator and that aircraft that's being simulated is moving in space, or it's turning, or it's firing a weapon or something like that, then it will output all of those changes as they occur. And it's up to every other system to capture that data, to receive that data, and determine whether that is of interest to that system or not. So the aircraft in a flight simulator may very well be of great interest to a radar, but if you had a medical system also as part of the network, then you would say, well, it's probably not particularly interested in the aircraft's changes in position. Here's an example of the DIS PDU that I was describing earlier, a specific example. So you'll notice here on the left in the blue, it says there's a U.S. Air Force F-16C Falcon, and that's identified specifically by the enumerations of 1, 2, 225 for country, 1 for category, 3 for subcategory, etc. So when you send those numeric patterns across the network, you are identifying a U.S. Air Force F-16C Falcon. And by contrast, if you were talking about a U.S. Air Force F-22B Raptor, then you see that the numbers are similar in some ways. It's still a U.S. Air Force, and it's still an airplane. So the entity kind is a 1, the domain is a 2, the country is 225, indicating the United States. But when it gets down into the subcategory and the specifics, the numbers are different. The high-level architecture, or HLA, can be described as a set of services for simulation data exchange and coordination that's provided by a runtime infrastructure. These services are accessed through a standard interface. So a data model, in this case called a Federation Object Model or a FOM, is expressed in a standardized text file using the XML standard, and that text file defines how the objects interact with each other. The information exchange is governed by Federation agreements and supporting Federation Information Data Exchange Models, or IDEM, and this describes when and where and how to utilize the service in order to distribute the data around. HLA is flexible that it can be used for different types of systems. So it could be used certainly for military combat systems as it's most commonly used for, but it can also be used for transportation, medical, space, those other examples that I've given before. And all of that is just defined in the Federation Object Model and the IDEM data exchange. HLA uses commercial off-the-shelf and open source business models. The standard itself is open. Anyone in the world can use it. And there are commercial companies that provide tools and utilities for work with HLA. So you see the description down at the bottom. The RTI provides the services and presents a standardized HLA API to all of the federates that are sharing data and running together. So in coming back to the example I used before, those federates, one of those might be a flight simulator, another one might be a second flight simulator, another one might be a tank simulator on the ground, another one might be a radar simulator, etc. And they're all working together and exchanging data. DIS and HLA data models are standardized through the IEEE, that's the external standards body for the Simulation Interoperability Standards Organization, or CISO. So CISO works to develop these standards and to maintain them, and IEEE acts as the controlling body to make sure that they are kept standardized. So you'll see here at the top things such as physical entities and aggregates, radios, logistics, all those things are objectified, kept in an object reference sort of a way, and therefore HLA in its real-time platform reference FOM, or Reaper FOM as it's called, which is the most common FOM for use of HLA systems. And that is a FOM that developed from the earlier DIS standard to make it easy for DIS systems to exchange data with HLA systems. The DIS and HLA standards are maintained through the CISO organization. You'll see here that organization consists of government, industry, and academia. It also consists of commercial companies, government organizations, open source contributions, etc. And these work on the standard, they work on the services, and extend this over time. And the IEEE, of course, is the external standards body for CISO. Now, to compare that with TINA, I'll hand the presentation back to Kurt, as he is much more expert in TINA than I.
Thank you, Damon. So real quickly, one of the big things that TINA was focused on the early days is range integration architecture. And what that means is whether it's a test range or a training range, everything happens real time. So performance was a big focus on the early versions of TINA, and they've continued to develop it that way. So performance was a key aspect of it. The second key aspect of TINA was that it was a government off-the-shelf solution, so that government organizations and industry and international partners can use this set of free software and solutions to enable their interoperability requirements. So what does it provide? A lot of the things that Damon's talked about: interoperability, common data models, integration of LVC assets, common reuse of capabilities across the different test and training organizations. And so what's included in this TINA architecture? Well, we've talked about object models, and that's what these data contracts are. There's a set that people can use to describe what they would find on a test and training range. And one of the things that TINA does is it takes that data model and then generates software based on that generates software based on that data model, so its users can quickly code to this TINA standard. And if we have a set of common object models, then having a set of tools that use those common object models that everybody can use free of charge was also part of the mandate of TINA. And then being able to composition reuse is a big forcing function / driving requirements of why TINA was developed. TINA is continuing to be evolved, and it does have institutional government funding, so it'll be here for future needs. Next slide, please. So let's talk a little bit about this interoperability. On the right-hand side of the slide, it talks about data management and event management. Those are some of the solutions that the TINA architecture provides. We talk about LVC integration. That's some of the enabling properties of TINA. And then at the bottom, sharing and reuse. How does TINA enable sharing and reuse? So back up top at data management, we have common specifications or data model for all the test and training data that one might want to collect. We have there's a high performance ability to data distribution across those different applications and computer platforms using different computer languages, both to come to mind C++ and Java. And it also is able to manage different classification levels. Event management, there are an ability to have local and remote command and control of different simulations and LVC assets, and it has built-in health and status monitoring. It can support real-time simulation and stimulation of live sensors and instrumentation. And it connects not in interoperable and inter and intra range systems. So what that means is there are solutions in place from the TINA organizations that you can use to communicate with long-standing range solutions that you want to interoperate with, so that you don't have to develop an application to communicate with those legacy systems. And sharing and reuse, very similar to DIS and HLA, eliminating proprietary interface to range instrumentation is key because we have these common object models and an API. Sharing and reuse of common range tools and capabilities, well, you go to the TINA website and download these solutions and you can use it. And then online collaboration and file sharing. There's a whole suite of tools that will allow other users to leverage what other folks from around the country, community have used. Next slide, please. So this is a graphic of what TINA provides. Let's start in the middle. The TINA middleware is that data distribution service that allows data to be sent from different applications and LVC systems across an environment. And so whether you're talking to a range resource application like a radar or a simulation or a hardware in the loop, there's connectivity through the API to be able to talk to the TINA middleware that over the network. And so everything above the red line are all the different applications that have been TINAfied on a test or training range, to include simulations, live assets, and virtual assets. On the bottom side, you'll see TINA utilities and a couple other things there. Those are the tools and solutions that the TINA project provides so that the TINA community doesn't have to develop systems on their own. And that includes repository utilities, object model utilities. TINA provides a suite of gateways to enable it to communicate with HLA and DIS and other legacy range protocols that you see across the test and training ranges, and then common data collection capabilities. So if you have a common object model, common middleware, then it's really easy to build these tools that you can share across the community. Want to highlight there is a commercial URL, www.tina-sda.org, and that will take you to another website where you can get registered and download everything you might want to learn about TINA. Next slide, please. So one of the things that is so important, and I hope Damon and I are getting this across, is having standards being managed by standards bodies is so important. So the DoD is maintaining the TINA standard object model. And the object models were initially based on live test and training range requirements. Virtual and constructive simulation requirements are now included. And there is an organization called the TINA Architecture Management Team, or the AMT, and it's comprised of government, industry, and academia. And that group, the voting members, are the ones that manage the open standards for TINA. And the organization that funds this is the Test Resource Management Center, or TRMC. But so again, where HLA and DIS chose IEEE to do their standards, TINA used a government organization called the Architecture Management Team under the Test Resource Management Center to manage the TINA standards. Next slide, please. Looks like it goes back to you, Damon. Over to you, sir.
Thank you, sir. So now let's look at a recommended integration approach to make all these things work. First of all, identify a common architecture. Utilize a horizontal integration using an enterprise service bus concept, such as HLA, TINA, those others we've described, whenever possible. An enterprise service bus will provide the ability to meaningfully communicate for reuse and composability. So it's possible to put a system together that maybe has a simple model in one location, and then later on substitute that simple model for a more advanced model, and to do so without perturbing all of the rest of the system, making it very easy to do that because of the underlying architecture. A standard data model will describe the data that's communicated, A standard services interface or an API is the software providing the standard services to support those data models and data interactions, and those services will distribute the data throughout the network. These subsystems are called federates, and the integrated system is called a federation. So here we have 5 orange federates in a single federation. The integration process has been studied and formalized very well by the IEEE in a standard. You see the number there, the IEEE recommended practice for distributed simulation engineering and execution process, which we just call DSEEP. This is a recommended practice for doing such types of systems and developing them and providing a multi-architecture overlay and a process for developing these things. It also encompasses TINA concepts of operations in the TINA environment, rather, for similar types of overview activity. The HLA distributed simulation engineering and execution process, DSEEP overview, let's say, was developed based on authoritative systems engineering processes. And these have been adopted and extended to address the types of requirements that are commonly encountered in distributed simulations. We can identify and describe the sequence of activities that are necessary to construct and run simulations. This process is also relevant and can facilitate the development of those simulations. But a key thing is that it is independent of interoperability architecture. So the process does not require a particular underlying architecture. The process is more a formalized way of getting a grip on the problem and working through the steps of the problem so that the solution is well architected and then can be well implemented. There are various tools that can help with the communication of the data flow and the data interactions in systems. And of course, the bigger the system, the more complicated these things can tend to look. So having some good tools and organization really helps. So we can have things like an interface matrix, connectivity diagrams. You'll see here examples that appear to be implemented in something like a spreadsheet, and then others that are done in visual tools. These are all effective at communicating the event design across the team so that everyone that's involved can go to these source documents and be sure of how the system is meant to be both architected and working. So the key data includes the location of data, IP addresses, ports, protocols, etc., and the messages, and obviously the names of data and things as well. So these types of tools can be very handy. It is very common to have interoperability involving gateways between systems of different types. Some of this is brought about by simply having one system that was built at one time and another system that was built under different circumstances at a different time, and then finding a need to put those two things to interoperate. So in order to do that, complex LVC environments may require interoperability between systems that have fundamentally different architectures. In that case, we're required to use something that is commonly called a gateway. And these are bridges, another term for that purpose, between different simulation architectures. So for an example, we could have TINA at a test range interoperating with other DIS or HLA systems, or both, as Kurt referenced in his slides earlier. Or we could have a legacy DIS-based system, which is interoperating with a newer HLA-based system, as you sort of see here indicated visually at the bottom of this slide. When using gateways, they at first seem to be very handy, but they do have to be used with caution. A gateway will translate data and services between different middleware or between different object models and services. And it can also be used to filter data in the process so that some data is transferred while other data is blocked. And it can be used to log the data and monitor the data and detect and notify the system about errors or other issues that arise. However, when placing a gateway between two different federations or two different large systems, in many cases, you might create a single point of failure for the whole system. So careful system design really has to be thought about when you're considering the use of a gateway to minimize that potential problem. So a top-level system design trade-off analysis has to consider schedules and costs and technical factors, etc., and they have to determine the best way between two different implementation methods. One is just select a common architecture for the entire environment. In other words, put everybody on the same baseline. Life is going to be good. That's going to work well. Or take what you have, implement, integrate, and test, and operate with some gateways in between. And if that's done well, that will work well. If that's done poorly, the whole system will suffer. So interoperability using gateways, again, the commonly used gateways are available as commercial off-the-shelf products from numerous vendors. We urge you to check carefully, though, that the list of supported features of various gateways, in fact, match up to the requirements that you have. So that is an important thing to do. TINA-related gateways can be downloaded from the TINA website, as Kurt mentioned earlier. Sometimes unique modifications are needed, especially when a gateway is interfaced to some older or stovepipe, single-purpose, non-standards-based type of system. You see the unhappy face there. Sometimes that's just required, but wherever possible, it would be nice to avoid that. Let's talk for a moment about multiple levels of security. And first, a couple of definitions of terminology. A security domain, we mean a system or a group of systems operating under a common security policy. So a security domain might say a secret system or a top secret system that's working all unto itself. And a cross-domain solution, which is also sometimes referred to as multi-domain operations, is an information assurance solution that provides some ability to access or transfer information between two or more different security domains. So therefore, we can engage in systems that transfer data between unclassified, secret, top secret, etc. type of systems. When establishing a complex distributed environment, the information transfer between two or more security domains may be needed. That's probably obvious to everyone. Most organizations don't have an effective means to address this issue because it is very complicated and it's sometimes hard to solve in a general way. So as a result, too often the solution is a brute force denial of access to information, such as simply saying no data shall leave the secret system and go into the unclassified world. Well, that usually means that there'll be no interoperability and loss of training, etc. Perhaps even negative training in those cases. But nevertheless, that's sometimes what's done is they just simply say brute force, deny all access to information. And as I said, that severely limits the system effectiveness. So the purpose of a cross-domain solution, on the left, highlighted in green, is a low security domain network. On the right, we have a high security domain network. And a better way of doing this is to apply some sort of rules and some filter decisions so we can block the data or we can sanitize the data or we can decide what data to pass back and forth in either direction. And we can also apply logic and math and comparative operations to figure out what to do to meet the security requirements. So this can be done to enforce a relevant security classification guidance. Therefore, the default state is to block all traffic, but the data owner guidance is implemented through these user-definable and event-specific rule sets. So the rule sets can apply, as I said above, logical operations, math operations, and comparisons to determine how this data should be transferred. Here's a CDS example involving multiple protocols. So here we have an HLA source and an HLA TINA system on the left interfacing through a cross-domain security in through another HLA or TINA gateway product into an HLA environment. So therefore, we have a classified network on the right interfacing with an unclassified network on the left, according to some rules, as we pointed out. So these two federations are running in different security domains, and each one is using HLA to interoperate. This example meets the requirements for the cross-domain security, but it also has a native TINA interface available as well. Gateways are used in this case, and this approach requires HLA-based environments to use the TINA-based cross-domain security protocols. Now we'd like to move on to taking a look at a specific LVC interoperability use case. So we start with the task at the beginning was that we had a ground-based command and control system, a C2 system, that is being enhanced and needs to be tested. So the present test method stimulates the C2 system under test with real data sent from a live aircraft across a radio data link. So this is a very expensive way to test a ground-based system because it requires an aircraft in the air dedicated to the testing. So great savings obviously would be achieved if the test used a flight simulator instead of a real aircraft. In this case, an available flight simulator could be used, and it had a Link 16 data link processor interface, so we could get data out of that and connect it. And the flight simulator, therefore, could be used to stimulate the C2 system. And that all sounds great. It seems like the problem is solved. It's not quite that easy in real life. The real-world analysis of this system revealed that the flight simulator had an older HLA interface that had never been kept up to date. And it uses a vendor-modified version of the Reaper-FOM. And I come back to that reference we've been making before of avoiding stovepipe systems, where in this case, it was not built entirely on the standard interface, but rather was modified heavily. A scenario generator with both DIS and simple interfaces is available to insert simulated tracks of other aircraft into the network for testing, so that's good. And the data link processor has an interface to the simple program, so those two things can talk together. But the Link 16 data was found to be represented in two different ways. Again, a standards-based implementation and another, unfortunately, non-standards-based implementation. So by applying the DSEEP analysis that we referred to earlier, a feasibility study of this system suggested that if HLA were used as the common interoperability solution, it would provide the common architecture to bring these systems together. And we could insert an HLA to HLA bridge to connect to the older system that had not been kept up to date. And then we could use a gateway going from HLA Reaper-FOM standard environment to the DIS environment so that we could connect with the scenario generator. So multiple translations going on there, but that all seems to work. But in order to do so, we would have to accept some limitations. First of all, the simulator data would have to be accepted as the ground truth. We don't have the aircraft in there anymore, so the initial assumption is that the simulator is correct, essentially. And J messages coming out of the flight simulator will not be bridged. Those are specialized data messages that in this case will not be bridged. And also in the initial implementation, there will be no voice communications. So you can see the system's getting a little more complicated in its drawing, but it's beginning to come together and provide a mechanism for passing data from end to end. So by doing a spiral of integration tests and development, this demonstrated that selecting HLA as a standard was in fact appropriate due to the HLA technology and the performance, but also the existing HLA solutions and experience that were available. The Reaper-FOM extensions, the HLA disk gateway, and the HLA to HLA bridge concepts were acceptable throughout. A problem was encountered when it was noted that the disk network did not work exactly right due to computer clocks not being in sync. And since those were on different government systems, they required different permissions and things to work out to get those synchronized. So that took a little work. And then the scenario generators just worked in one direction. Also, the security aspects needed further analysis beyond the initial tests. However, this was declared a success because the initial tests produced good results, provided we kept in mind the previously known limitations. It was later decided that additional actions were required, such as updating the scenario generator's DIS interface would improve things. Certainly, as I mentioned, getting approval from the authorities to synchronize the computer clocks was required, and getting approval to run tests with a dedicated Link 16 network and the participating aircraft on the ground so that the flight simulator could be used as a substitute for the real aircraft and vice versa in order to validate the data. So in summary now, we look at standards overall. As we've talked about today, there are several standards available for live, virtual, and constructive interoperability. Some are especially made to support simulation, and some are focused on use with live systems. These standards need to be maintained and updated. That's done through the standards organizations that we have described because, of course, new requirements emerge over time. Standards need to be balanced between stability on the one side and flexibility on the other side. They have to be stable enough to allow systems to be developed that support the same version of the standard. That really helps everyone involved. But they also have to be flexible enough so they can be useful and support current requirements plus new and evolving requirements. So somewhere always walking between locked in stability and total flexibility is the right answer. And this is the work of the standards organizations. Standards should not be selected only on technical merits. Too often this is a problem that has bedeviled a number of programs over the years. It helps that there's a community of users that have used all of these standards and know where they apply and how they apply and which situations where they work well. It ensures the long-term use of a standard and avoids obsolescence, which benefits everyone involved. And it promotes evolution of the standard and provides a communication forum about the standard and about applications. Industry support in the marketplace, trade shows, etc., is very important. Government and commercial off-the-shelf products come about through that process. These generally cost less than custom-developed solutions. It also provides for on-demand training courses, technical assistance, and aids in the adoption and the evolution of the standards. Organizations in general, our summary is that they should try to use a limited number of interoperability LVC standards. If you try to use everything that comes along and declare it as yet another standard, it may ultimately find that you don't have any standard. Deviations, however, must be expected to fit unusual situations. And this will develop in-house skills and experience that will be needed on future programs and can help in the adoption and development of gateways as an initial approach to integrate these disparate architectures. Integrating LVC via distributed simulation is a powerful capability. That's been well demonstrated. LVC across domains involving multiple military groups creates operationally realistic environments, and we see that more and more every year. Supplementing a single system with other LVC systems greatly enhances the realism of training and does produce a system whereby the whole is greater than the sum of its parts. Integrating C2 systems with LVC systems builds environments that are operationally realistic, so we can indeed train as we fight. Standards enhance integration and reuse of other LVC assets, tools, and technologies. As a result, these standards eliminate or greatly reduce time, cost, and performance risks, especially to develop something that ultimately might turn out to be a single-use stovepipe, very expensive, and soon obsolete type of system. Standards-based instrumentation and management functions within an environment provide coordination of planning and execution, and that helps all the people that are involved in these systems. So the bottom line is that leveraging the standards that are out there and the use of existing networks allows program managers to do more with less and not have to invent everything entirely from scratch. So in summary, our last slide is we'll say that distributed simulation has advanced greatly since the first attempts in the 1980s. Simulation developers today can establish LVC environments very quickly to solve very complex problems at the system of systems level. The selection of the appropriate architecture requires some careful analysis and thought, whether it be DIS, HLA, or TINA, specifically in the simulation community. And that decision is sometimes at the user's discretion, but other factors may favor one architecture over the other, such as, for example, a specific technical feature or the need to connect with systems already in place, or perhaps organizational policies. But be sure to choose between DIS, HLA, or TINA based on current information. All of these products have developed over a long period of time, decades literally, and it is very important to be up to date about what their capabilities are rather than make decisions on something that occurred back in 1986 or the year 2000. So the best advice overall is to get involved. Join in with the CISO organization and help to push these standards forward and let them grow and help to grow them into the future. Thank you all. Kurt and I appreciate your time.